Okay, hi everybody.
Hello, welcome back.
Oh, thank you. Hope you guys all had a good break. My time was a little bit extended. Did you have a question?
Yeah. Will we be getting our quizzes back before the final?
I've got 3 of them right here. I give these quizzes back. And then whatever, anybody who doesn't pick up their quiz now, we're going to give them back after, like when you turn in your quiz 4, we'll give the other ones back. And then we will get quiz 4 back, hopefully before the final. Don't quote me on that because we'll try to, it's just Dave and I grading because Dr. Boldy's out of town. So we'll try to get everything done and get those back. I'm not sure how exactly we will, but we will do our best to get those back to you guys. And then also we'll have the solutions to the quiz put up on the website. So even if you don't get yours back, you can still look over the answers. Okay? You guys have any more questions about the stuff like that? Just move this chair out of my way. Does anybody want a chair? Okay. So, do you guys want to start kind of most recent stuff first and work our way backwards, like normal? Okay. Well, we did exoplanets today, and this was kind of nice, right? To have something that was a little bit more understandable, that you could, wasn't quite so like out there. Yeah. So, I think that was kind of nice for everybody to get something that we could really envision a little bit better than just quark soup and universal expansion. So, there are a couple different ways in which we detect exoplanets. And the big one, the kind of first big one that they came up with was something called the radial velocity method. And the idea behind this is that we talked a lot about how you can have like 2 stars orbiting each other, right? And we talked about how you can look at their radial velocity curves and say, you know, how much bigger one is than the other based on these curves, right? The bigger star is going to have a smaller curve. So we're just kind of going to expand that concept and say, okay, what if this smaller star is actually so much smaller that it's a planet, right? And now you have a curve that instead of looking like that, you know, looks like this, but even more, right? One of these curves is way bigger than the other.
And so can you kind of tell that by knowing that, like, if it's smaller than 0.08 solar masses, then it can't be a star?
Yeah. That's a good way. We also, we won't see it if it's not a star. I mean, there are certain stars, like if we have a binary system and one of them is really bright and they're really far away, then we can't really see the other one if it's like a dim star. Mm-hmm. But yeah, we can tell their masses and say that, oh, it's too small to be a star. So, you know, why does this happen? When we think about the Earth going around the sun, we don't really think about the sun moving, right? We think about just the Earth going around in a circle. But what's happening is both of them are actually rotating around something that's called their barycenter, or their center of mass. So when you look at something called the center of mass, right, if you have something really big and something really small, this center of mass is going to be over here. You kind of average their masses and how far away they are from the center of mass, right? So if you have mass times distance, you know, you want them to be equal. So you want, this is distance from the center of mass, right? So if mass 1 is really big and mass 2 is really small, then mass 1 has to have a big or a small distance, and mass 2 has to have a big distance to equal each other, right? You have something really big and something really small is equal to something really small and something really big. Does that make sense? You kind of have to balance. If you have a big mass, you have a short distance from the center of mass. If you have a little mass, you have a big distance from the center of mass. You're kind of balancing out. So for the sun, the center of mass is actually inside the sun. It's not at the center, but it's inside it. So the sun is rotating about this point that's inside of it. So it's not really doing a circle, it's just kind of wobbling, right? It's going around a point that's like right here. So it's kind of just wobbling around this point. So any two objects orbiting each other are going to really orbit around the center of mass. But when you have such a big mass disparity between the sun and a planet, oftentimes the center of mass is going to be inside or really close to the big thing. Right? Again, you have a big mass, small distance from the center of mass. Small mass, big distance from the center of mass. You could have one big thing and one small thing. Right? So if something is orbiting around something that's really close to it or inside of it, it's going to make just a little tiny little circle or just a little wobble. If something's far away from the point that it's orbiting, it's going to make a much bigger circle. So you get this bigger curve for the thing that's small and far away, and this little curve for the thing that's close. But with planets, we can't really measure this because we can't see the planet. It's too dim. So all we see is a star that's going like this. Right? And there's no other star that's making it do that. So we know that it has to be a planet making it do that. Something is making it wobble. It's pulling on the planet and causing it to rotate around it. And the planet is pulling back a little bit and causing a little bit of a wobble. So this is the radial velocity method. We see a star that has a little wobble like this. Right? This is how fast it's moving towards or away from each other. Towards or away from us. So if something is on an orbit like this, and we're down here looking up at it, when it's right here, it's coming straight at us. When it's right here, it's moving straight away from us. Here, it's not moving at all towards or away from us. So this point is when it's not moving away. This is when it's moving away from us or towards us. It's going to be up here. When it's moving away from us, it's going to be down here. Okay, so we're just measuring, this is a measurement. It's turning this into a graph and saying how fast is it moving away or towards us. Right, so we have to be looking at it like edge on. We have to be looking at it. It's orbiting like this, and we have to look at it like that. Right, if we're out here looking at this, it's never moving towards or away from us. So this method only works for stuff that we're looking at kind of from this side of the orbit. Okay, so we see something that's got a little wobble. We know there's got to be a planet there. We can measure about how big the planet is from how big the wobble is and how big the star is.
Just to be clear, like if the circle there was our eyeball, is that what you mean looking at it that way?
This circle?
And that's the object we're looking at?
Yeah, so if it's orbiting like this, right? We can see it if it's orbiting like that.
Okay.
If it's orbiting like this, then we can't see this radial velocity measurement. The planet has to come like between us and the star for us to see this. Because if it's orbiting this way, right, in this big circle, then this star is going to be going in a circle like this, right? And it's never going to change how it's moving towards or away from us, because it's always going to be moving in the plane against us, right? If it's moving like this, it never changes how fast it's moving towards you. But if it's moving like this, sometimes it's moving towards you, and sometimes it's moving away from you. Does that make sense? Okay. So that is the radial velocity way. The other big way is from transits. So we have a star These do not erase well. And it's bright, right? Stars are bright. And again, this has to be kind of in the same setup, where it's the star is here and the planet is orbiting like this, right? Because what happens in a transit is the planet passes in front of the star. And so we have a star, and we measure how bright it is, right? If nothing's passing in front of it, it just looks like, you know, this is how bright it is. It just looks like that, right? Its brightness doesn't change. But all of a sudden, you have a little dark planet passing in front of it. It's going to be a little bit less bright, right? This planet's blocking out a little bit of that light. So we get a little bit less bright. And then, you know, it goes around. And then the next time it comes back around, it does the same thing. And this happens at really regular intervals, right? Every time this planet comes around, it gets a little bit less bright. And it happens once every orbit. Yeah? So this is the transit method. And he talked about it. It's a little bit more complicated than this because you have to deal with the reflected light from the planet. But this is the basic idea behind it. This planet blocks light from the star. It makes the star look a little bit less bright to us. And it happens really regularly every time it goes around. So again, like if the planet were rotating, you know, like this around the star, it would never cross in front of the star. And so we wouldn't be able to detect it with this method. It has to be going around where it comes between us and the star. Okay?
What is it that we're detecting, I guess? Because you said there was two ways. Like the first way is radial velocity and the other way is transit. But what's like, is it that we're actually...
we're detecting if there's a planet there.
Okay.
Yeah. So these are ways which we can tell, like, so from this, from how much dimmer this gets, we can get an idea of how big this planet is, right? Because it's a fraction, right? So this planet is blocking some fraction of the light. And if we know how much of that fraction is being blocked, then we can say, okay, we know how big this planet is compared to the size of the star.
And is that how we would tell the difference between whether it was planet A or planet B? If there were more than one planet?
If they're not transiting at the same time, then that's...
Or the size?
So size, also, like, how often, right? So, like, if you have planet A and then planet B is closer, so it comes in, like, more often, right? It's going to look a little bit different than planet A that is farther away, and so it only comes in less often, right? So planet B is closer by, it comes in front more often, so you get more of these dips. Yep?
Can you explain the conditions again for the distance? You said that something has to be in between us, like when you're talking about the distance from the planet.
Oh, so this basically just means that the planet has to come between us and the star for us to be able to detect it, right? Because if the planet is orbiting, so if you're looking at it like this, right, and the planet is orbiting around the star like this, it's never going to cross in front of the star, and it's never going to get dimmer. So we won't be able to see it if we're looking kind of top down into a solar system. But if we're looking at it from the side where the planet's going like this around the sun, then it's going to cross in front and we can see it. Okay? So those are the two main ways to detect exoplanets. We can also do something called astronomy, which is where we look at proper motions, and we just see that, like when I talked about that, it wobbles a little bit. So when it's moving transverse to us, like across from us, it kind of makes a little bit of a helix pattern. And that's one way we can tell, but that's not a very common way. And then the kind of new way that's really exciting, but hasn't had a lot of planet detections, because we're still kind of working on it, is direct imaging, where they take the planet and the star and they block out the light from the star, so they just kind of put something right here to cover it, and then you see the little light from the planet.
Kepler detects this transit.
Yes,
Yeah,
Kepler
this
detects
transit.
transits. Right. So, yeah, so for direct imaging, you block out this, and you're left with your little picture of your planet going around. And so for direct imaging, you want it to be this other way, right? You want it to be where we're looking kind of down onto it and the planet's going around that way, so we can watch it go around. So those are the main ways. Some kind of important things. Bigger planets are easier to detect, right? They make the star wobble more. A small planet makes it wobble less. A big planet makes it wobble more. So we can detect big planets easier. Planets that are like, and these also, like a big planet's going to cover up more of the star when it passes in front. So it's easier to detect that dip in brightness when a big planet comes in front versus like a tiny little planet that just makes it a teensy tiny bit less bright. So the most of the planets that we found are like Jupiter sized or bigger. They're called hot Jupiters because they're also most often closer into the star. Most planets that we find are close to their stars, like a lot closer than the planets in our solar system are. So that's really exoplanets. Oh, the other thing is the habitable zone. So around every star, you have something called the habitable zone. This is also called the Goldilocks zone because it's not too hot and it's not too cold. It's just right. Right? So you have your star, and it has to be far away enough that water doesn't just evaporate, but close enough that water isn't just ice. So it's just liquid water, right? You have your star, and then you have this area around it called the habitable zone or the Goldilocks zone. Right? So if you have a star that's cooler, this zone is going to be smaller. It's going to be closer into the star, right? Because you have to be closer into the star to get water to melt if the star is cooler. If you have a really hot star, the habitable zone is going to be all the way out here. Does that make sense?
Will the actual zone be smaller, or will it just be farther?
I think it gets bigger because of the 1/r² dependence. So as far as I know, it should get like wider as well. But I can check on that. I have a little simulation that I can link you guys to where you can change the temperature of the star and see how the habitable zone moves.
Oh, wow, cool.
So
the hotter it is, the farther away?
Yeah. Because you want, if you want water to be liquid and not boil or freeze. So if you got a hotter star, you got to move it farther away for it to stay liquid.
So then if the sun is getting hotter over time, will there become like more habitable places?
So it's going to just move farther out, right? So it'll get a little bit wider maybe, but in general, it's just going to kind of move farther out. So closer into the sun is going to be less habitable, and farther away is going to be more habitable. Right. Okay, so that is mostly exoplanets. We can look at the homework problems for this and see if I missed anything. Yeah. So 21, which of the following techniques are, oh, I did miss one. Okay. So another technique that is used is gravitational lensing, when we talked about how gravity can bend light around it. So if you have a star, and then you have, the planet is going around it like this. You have a star, and the light's coming off this star, right? And you have a planet come right in front of it. Then it's going to bend light around this star, around the planet, and all of a sudden this star is going to look brighter, right? Because before we were getting like one light ray off of it, but now we're getting light rays. You know, now we have 5 light rays coming from this we're here on Earth, right? These ones, they would go out this way, but they get bent around this planet and come to Earth. So we get, 5 light rays from this star where we would get 1 before, and all of a sudden this star looks brighter. Does that make sense? Okay. Right, this light would go out normally, but instead it gets bent around and sent to us. It gets bent around this planet. This one would go out this way, but it gets bent around and sent to us. So we get all this extra light that gets bent around this star. It would just go off and we wouldn't see it, but it gets bent around the planet and sent to us. So the star looks brighter. So that's the gravitational lensing method. Okay, so now that you know the answer to part of this, 21 says, which of the following techniques are used to detect planets orbiting stars other than the sun? So measuring small periodic radial velocity variations in exoplanet host stars. Is that something we do? Yes, that's that first technique we talked about. Measuring small changes in the total light from a host star when an exoplanet passes in front of the star.
Yes.
Yeah, that's that transit method. This is so recording. Directly imaging exoplanets and their host stars. Yep, that's one we do. And then that last one is using the boost in brightness of a background star when an exoplanet passes directly between the back star and the Earth and gravitationally lenses the star. Yes, that's that last thing. That light, instead of going off into space, gets bent around the planet and sent to us. It makes that star look brighter. So 22 says, which of the following are true and which are false regarding what we know about exoplanets as of June 2017? So although we have now discovered many exoplanets, to date we have not found another system with more than one planet.
False.
That's false, right? We found quite a few with more than one planet. The most common type of exoplanet discovered to date is approximately half the mass of Earth.
False.
That's false. How big are they? Great. They're about Jupiter size. Most exoplanets discovered to date are very close to or in the habitable zone of their host stars. That's false. They're super close to their stars. They're like inside the habitable zone. And then the majority of exoplanets discovered to date have been detected via light curve and the transit technique. That's actually true. So we've got the light curve, the transit has the most, and then radial velocity.
But this is the light curve and the transit technique.
So light curve is the transit one.
Oh,
Transit is when we look at the light curve and see that it gets a little bit dimmer.
got it.
And
So
then-
the difference between the bend and the light.
Oh yeah, so right. Light curve. Yes, in light curves around this, but a light curve is when we look at like the amount of light that's coming off the star.
Okay.
This is the light curve.
What's that called?
This is the gravitational lensing. So this is like bending. Thank you for that.
Yeah.
Because that can be confusing. Yes. This gravitational lensing, the light does curve, but it's not a light curve. When we say a light curve, we mean measuring the light coming off a star and plotting that. That's called the light curve of the star. Right? So transit has discovered the most from that Kepler satellite. Right? That uses the transit method, and that discovered tons and tons and tons of exoplanets. And then the radial velocity method. And then the other ones, the gravitational lensing, the astrometry, the direct imaging.
So this question, sorry, go
Oh.
ahead. This question is just referencing the transit method?
Yes.
Okay.
That's the most, right? Because the transit, this was that Kepler satellite. And that had the most.
Can you go over the third one, why it's false? Most exoplanets discovered today are very close to or in the habitable zone of their host.
So most exoplanets we find are like really close to their stars. So they're like inside of the habitable zone. Like not in the habitable zone. They're like inside
Okay.
where they would be. Okay, most of them we find are like super close in. And then, but we have found some that are in the habitable zone. It's just most of them aren't. It's pretty rare. So 23 says, which of the following statements are true and which are false regarding the habitable zone for exoplanets? So it is the region in possible orbits for exoplanets where the temperatures allow for liquid water. That's true. Not too hot, not too cold. For a smaller mass, cooler star than the sun, the habitable zone is closer to the star.
True.
True. Right. Cooler, you gotta be closer in to have water not freeze. For a given mass exoplanet, it is easier to detect the planet in the habitable zone of a low mass star than to detect it in a higher mass star.
True.
So this is true. So I told you that it's easier to detect planets that are close into their star, right? So for a low mass star, the habitable zone is close into the star. So we're going to find more planets in that close habitable zone. If you have a high mass star, the habitable zone is really far away, but we're still going to find planets that are close in. So they're not going to be in the habitable zone. Right? We're going to find planets close in no matter what. So you just have to ask, is the habitable zone going to be close in, or is it going to be far away? For smaller, cooler stars, it's going to be close in, so it's going to be around where we're going to find the planets. Does that make sense? Okay. And then, the only planet known to exist in the habitable zone of a star is the Earth? It's false. We found a couple in the habitable zones. Not too many, but we found some.
I have a question.
Yeah.
Does the mass always determine the temperature of the star?
Generally.
Okay.
I mean, there's like some change as it goes through like the different cycles, but like on the main sequence, mass and temperature are really closely related.
Okay.
And then it depends on like what type of star it is. If you know what type of star it is, like if it's a giant star or on the main sequence, you will know how mass and temperature relate to each other. It's not the same relation, like the relation between mass and temperature for a main sequence star is not the same as that for a giant star. But if you know, okay, this is a giant star or this is a main sequence star, then you know how the two relate to each other.
Remember, you were saying that we know more hot Jupiters,
Mhm.
but this plot from the lecture showed
Yeah,
a lot
so
more hotter.
that one, what is the date on that one? It should be up in the corner of it.
Oh yeah, 2016.
Yeah, so there's a 2019 plot a couple slides ahead of that.
Okay.
So I think the one that you were talking about, that shows what we kind of expect to find. Like we expect to find a lot more super Earths because those are kind of easy to form. They're smaller. But as far as I know, going off this 2019 plot, we have more Jupiter-sized ones. Right, so this is, it's on slide, like 45. There's a plot from November 21st, and it has most of them clustered around one Jupiter mass. Yeah. Okay. I think that's all I have to talk about for exoplanets. Let me check really quick, see if there's anything else I want to say. So, yeah, so we expect most stars to have a couple planets. So there should be more planets than there are stars, right? And most of the ones, we found a lot that have more than one planet, but most of them have less than the number of planets in our solar system, which is 8, right? So I think he had some thing in here where he talked about how many. Sorry, this is loading really slowly. Yeah, so on average, there's 1.6 planet per star. 21 of them have at least, 5 planets. 5 of them have 6 planets. There's only one other one that we found that has 8 planets. So most of them have, it seems like 5's a pretty common number for number of planets. Some of them just have 1 or 2. But also, because, like, size, like, bigger planets are easier to detect, so there may be a lot more smaller planets that we're just not detecting. Because you have to be looking at it from the right angle, right? For some of the methods, they have to be going like this. Some of them, they have to be going like this. Like, we may just be not detecting them because they're not at the right angle. So, just the planets that we've detected are not all the planets that are out there. They're just the best ones that we can detect with our methods. Okay? Do you guys have any more questions about exoplanets?
Just a general question.
Yeah.
What is the criteria for something to be considered a planet?
So a planet has to, one big thing is that it has to clear its orbit. So this is why Pluto is not a planet. So when you are going around a star, there's a bunch of stuff out there. There's like other rocks, there's asteroids and stuff. And a planet has to be big enough that its gravity kind of clears a spot in its orbit. So there's nothing else hanging out in there. So it either like pushes or pulls all the other stuff. So Pluto goes through what's called the Kuiper Belt. So there's a bunch of other stuff hanging out in the orbit of Pluto, which is why it doesn't count as a planet. So it has to be, it can't be big enough that it has fusion, right? If it gets super, super big, then it's gonna get really hot and it's gonna start fusing and it turns into a star.
Okay.
So it has to be, smaller than a star, but big enough that it can clear its orbit. Okay? Any more questions about exoplanets? There's some more criteria. I just know that those are 2 kind of big ones. Okay. Then, I guess we can talk some about expansion and dark matter and all sorts of fun cosmology stuff that doesn't make any sense. So, anybody? Woo! Okay, so I'm going to talk about expansion, I guess. We'll do that and then we'll do dark matter.
Can we talk about number 5? That's on expansion. Oh.
Yeah. Let me pull the homework up. It always takes so long to post down homework up. So, we learned, so we'll talk about inflation and expansion. So we learned when we measured, not we, but scientists measured the recession velocities of galaxies, they noticed that all of the galaxies, except for a couple that are close by, so most of the galaxies are moving away from us. And the farther they are away from us, the faster they're moving away. And we determined from that the universe is uniformly expanding. So the problem was, if you just roll back that expansion, it doesn't answer all of our questions. So one big question that they had was called the horizon problem. And this has to deal with that cosmic microwave background that we talked about. Are you guys comfortable with that? Do you want me to go over that first, or do you feel okay with the cosmic microwave background?
You can go.
Okay. So as we look farther and farther out into space, we're looking farther back in time, right? Because that light from farther away took longer to get to us. So it was sent farther back in time. So what we're seeing is an image of a long time ago, right? So the farther a galaxy is away from us, we're seeing it how it looked like when that light was emitted. So a galaxy that we're looking at that's really far, that looks young, right now has evolved and done lots of stuff, but we see an image. It sends out this image of itself as a little baby galaxy. And by the time it gets to us, it's been a long time, and we get this image. So when we look farther and farther and farther away, we see farther and farther back in time. Does that make sense? Okay, so that means that we should be able to see all the way back to the start of the universe, right? If we can just look farther and farther and farther away, we should be able to see all the way back to the Big Bang. Except something gets in the way. So around 380,000 years after the Big Bang, the universe was kind of foggy. So you had protons and electrons just hanging around, right? So a proton, we talked about, how we looked at the abundances of the elements at the end of Big Bang nucleosynthesis, and we saw that hydrogen is the most common element in the universe, right? So a hydrogen atom is a proton and an electron. So oftentimes, the electron doesn't really matter. What makes it hydrogen is that one proton. That hydrogen nucleus is what defines it as hydrogen. And it can have electrons, and that makes it, ions. But what makes it hydrogen is that one proton. So sometimes when I talk about a single proton, or I say hydrogen, they kind of mean the same thing. So when we say that the universe was mostly hydrogen, that's kind of the same thing as saying it was mostly just a bunch of protons. Does that make sense? So it's these protons and electrons. They're going to combine to make a hydrogen atom. But right now, they're a hydrogen nucleus, which is just one proton, and an electron. And they're just kind of floating out around. And light comes through, and it starts bouncing off these. And it gets all mixed up. Right? So what comes in comes out all mixed up, and it looks foggy. So we can't see past this kind of soup of protons and electrons, right? Does that make sense? We can look back to when the universe was like this, the last time the universe was like this, and we can't see any farther because the light that was emitted before then got all mixed up when it was like this, right? So we just see this fog behind all the galaxies, right? This happened before galaxies were formed. The universe was like this. So if we look past the galaxies, we get to this fog of protons and electrons. And then eventually these electrons join up with the protons, make a hydrogen atom, and then they don't bounce the light anymore. So this light, you know, you going through time, these atoms, the light can just kind of pass through. So we can see, looking back in time, to right here.
And we would define that at 3, like as kind of a singularity at 380,000 years. Like
Yeah, that's when this happened. It went from being this just fog of protons and electrons to being atoms that we could see through. This is called the surface of last scattering. So before, it was the surface of last scattering is the last time you had this fog. We can't see past the front of the fog into older times of the fog, right? We can only see just that front edge of the fog. So everywhere we look, no matter what direction we look in, behind all the galaxies is this fog. Right? Does that make sense? So that's called the cosmic microwave background. So this fog was really hot. It was like 3,000 Kelvin. But the light from this had to travel a really long way to get to us, right? It's from really a long time ago, and it traveled a long way to get to us. And along that whole way, the universe is expanding and stretching out. So the wavelength of this light gets stretched out with the universe. So we learned about the Planck curves, right? So back in the beginning, we had this formula that said temperature is equal to 0.29 over your peak wavelength, right? So as wavelength goes down, as wavelength goes up, so this light is getting stretched out, and its wavelength is going up, right? We've got this curve, and I'm just stretching it out, and that's making the wavelength longer. As wavelength goes up, temperature goes down. So this emitted light that had the wavelength that corresponded to 3,000 Kelvin. And along its way to us, it stretched out, and by the time it gets to us, when we plug it into this formula, we get like 2.7 Kelvin. So what we see is a fog at 2.7 Kelvin. It used to be at 3,000 Kelvin, but we're just viewing it at 2.7 because of cosmological redshift, right? This wavelength has gotten longer and redder, so it looks cooler. Does that make sense? Yeah, so
Like the last part.
yeah, just this sent out wavelength of light that, looked something like this. And as it's traveled to us, the universe has expanded. So it's kind of like grabbed both ends and stretched. So by the time it gets to us, it looks like this, right? And so this longer wavelength looks like something at 2.7 Kelvin, but it was emitted at 3,000 Kelvin. Yeah, so it got longer wavelengths are more red, right? We have our rainbow. This has shorter wavelengths, this has longer wavelengths. So when we say the wavelengths got longer, they got more red, so they got red shifted. Wavelengths get shorter, they get more blue. Right, we talked about this with the Doppler effect. It's a very similar thing. So it's not, you can kind of think about it like these light waves cooled off as they traveled through space to get to us because they got stretched out. They were emitted at 3,000 Kelvin, and by the time they get to us, they've cooled off down to 2.7 Kelvin. Okay? So everywhere we look, behind all of the galaxies, we see this fog at 2.7 Kelvin. And that's the cosmic microwave background. And just about everywhere we look, it's at this same temperature. There's just tiny little variations. Some spots are like 0.000000001 hotter, and some spots are 0.000000001 colder than that average temperature. But overall, it's about that same, and then there's just tiny little portions that are just a tiny little bit hotter and a tiny little bit colder. Okay? So that's the cosmic microwave background. And it's everywhere we look, behind all of the galaxies. Behind everything. Yep.
So the cosmic microwave background is, what exactly is this phenomenon of the light traveling to us while the universe is expanding?
Right, so that's the redshift of the cosmic microwave background. What it actually is we're seeing this time in the universe when light was getting mixed around and scattered around and bouncing off of these electrons.
So that picture right there with all the messy lines.
Yeah, what we're seeing is this. The light gets scattered around and mixed up, so it just looks like a fog.
And that's called, sorry.
What we're seeing here is the surface of last scattering.
Okay.
So the cosmic microwave background is like the image of the surface of last scattering.
Do we have to know, say for the exam, what time it starts at, the 380,000?
That would be a good idea to know roughly. You may not know I would not expect you to have to spit that number out, but if I ask you what happened at 380,000 years ago, then you would say that's when the electrons and the protons joined together to make atoms, and the universe became transparent.
Or the last scattering.
Yeah, or that's the surface of last scattering. But what happened at the surface of last scattering was the electrons and the protons stuck together and made an atom, and instead of light bouncing around, it just goes through it. So it becomes transparent to light.
And it's called the
Cosmic microwave background.
cosmic microwave background.
The cosmic microwave background gets redshifted to 2.7 Kelvin by the expansion of the universe. So there's a couple homework questions on this specifically. I think. Okay, so there's 15 that says, what was the nature of the transition in the universe that reoccurred around 380,000 years after the Big Bang? So one answer is the end of the era of nucleosynthesis. No, electrons recombined with hydrogen nuclei and the universe became transparent to electromagnetic radiation. Yes. That's exactly what happened then. The first stars were formed. No, that happens later. Quarks combined to make protons and neutrons. Does that happen before or after this?
Earlier on.
Yeah, way earlier on, right? Because we got protons here, so it had to be before this that the quarks made protons and neutrons. So 17 says the temperature of the gas in the universe at the time it became neutral. So that's also what happened here, right? So this, you've got positive and negative things. This, hydrogen atoms are neutral. You have a positive thing combining with a negative thing. They cancel out, and it becomes neutral. So the temperature of the gas in the universe at the time it became neutral was about 3,000 Kelvin. Why does the cosmic microwave background appear to arise from a 3 Kelvin source?
It's because the wavelength stretched to
Right.
appear cooler.
Yes, exactly. This redshift happened. The wavelength stretched out because of universal expansion, and something with a longer wavelength appears cooler. Right? This formula that we used in the very first part of this class. If wavelength goes up, temperature goes down. Okay?
Can you explain that one more time?
Yeah, the whole.
Just like the sentence that you just said.
Oh, so just this, we have a formula that says that the temperature of something is equal to 0.29 over its peak wavelength. So the peak wavelength of the cosmic microwave background went up, right? As it got stretched out, its wavelength got bigger. So if wavelength gets bigger, temperature gets smaller. So it looks like it's cooler than it actually is.
Do you have that rubber band?
Huh?
Do you have that rubber band that you use?
I don't think so. I think I took it out when I did everything for Thanksgiving. But I can check. Oh, actually, maybe I do. So this is kind of hard to see, but sorry, guys. So on here, on this very tangled up rubber band, I have a wave drawn, right? I can kind of walk around, right? I've got a wave drawn on here. So if I stretch this rubber band, this wavelength gets longer, right? If I go from here to here, this stretches out the wavelength, and the distance between the tip of two waves gets bigger. So that's what's happening. This wave is traveling to us, and space, the rubber band, is stretching, and it's making this wavelength get bigger. Okay, so nothing, the wave itself isn't doing anything. It's space that's stretching out and making this wave bigger. Okay? Here, I'll do it for the camera. I don't know if they can see me. Ta-da! Okay, so the universe expands. That expansion stretches out the wavelength, and that makes it appear cooler. Okay? So that kind of leads us into what is called the horizon problem. So everywhere we look, the cosmic microwave background is the same temperature, right? There's just teeny, tiny variations, but generally, we can look at one side of the sky and the total opposite side of the sky, and they're the same temperature. And that's weird, because we know that in general, if you want things to be the same temperature, they have to kind of be able to touch each other, right? If you have something really hot and something really cold, and you touch them to each other, heat's going to flow from the hot thing into the cold thing until they get to the same temperature. But if you have them far apart from each other, they're going to stay one hot and one cold. So things generally only become the same temperature if they're close enough to touch, or to have a couple things, go between them and touch. So how is it that if we roll back the expansion of the universe to this time, the two sides of the universe that are the same temperature are not touching each other, but they're the same temperature? So we say, like, how does one side of the universe know what temperature the other side is at if they were never close enough to get to the same temperature? So they must have, at some point, been close enough. They must have been really, really, really close, and then they got really far away really quickly. So this is this idea called inflation, right? We know how fast the universe is expanding, but at some point in the past, there was this time, just a little short time, where the universe got a lot bigger in a really short amount of time. And then it just kind of started slowly getting bigger, right? So it went from really close and got a lot bigger, and then just kind of slowly started getting bigger. And back when they were touching, the two sides were kind of touching close enough to get to the same temperature when they were like this, and then they got shoved out to either sides, and that's the reason that they can be the same temperature. So it's called the horizon problem because They say that like particles over here or like light waves over here are out of the horizon of ones over here. They would have not been touching if we didn't have this big expansion, this big inflation part.
They would have been.
They would have not been touching if we didn't have the inflation. Like if we didn't have inflation, they would have only gotten to like this close, right? But if we had inflation, then they could start out here, then get this far away, and then go like we know them to be, moving away from each other like this.
So this only happens with 2 points that are like directly across from each other. Like it can never be like a point that's like in the center and then something.
Well, they're all the same temperature. But a point that's in the center and a point that's over here might have been close enough to get to the same temperature.
Because that's why we're seeing the 2.7 everywhere we look, is because it's all
Yeah,
the same.
everywhere we look is this 2.7.
So this is the uniform expansion.
This is the 2.7 is the uniform cosmic micro background.
Okay.
But it's also uniformly expanding. Uniform expansion just means everything is moving away from each other.
Okay.
Right? So yeah, so a point that's in the middle and a point that's on the side are the same temperature. But maybe they would have been close enough. But a point that's over here and a point that's over here would never have been close enough if they didn't have this point where they were really close and then they got really far away from each other. Right? So this inflation solved a lot of problems. It solved that horizon problem. One thing that they were kind of confused about is the flatness or the geometry of the universe. Is the universe flat? Is the universe like a big sphere? How is space-time curved? And in order for our universe to kind of make sense, they figured it had to be pretty flat. If it were curved, it would have been created and then gotten big and then maybe gotten to its maximum point and then crunched back down. And that didn't happen, so we know maybe the universe isn't positively curved. If it had this kind of saddle shape, this negative curvature, then it would have gotten bigger and just bigger and bigger and bigger and bigger and bigger and bigger, and maybe like galaxies and stuff wouldn't have been able to form at all because everything would just be too far away from each other for like gravity to pull them together. Because gravity has to fight against expansion, right? Expansion is pulling everything apart. Gravity's pulling them together. So if expansion happens too fast, then gravity can't pull things together and you can't form galaxies. So you have to have this balance. And the balance only worked if the universe was flat. And if you have inflation, we get a flat universe. Right? It's kind of like if you blow something up really, really big, like on the Earth is curved, but to us it appears flat, right? Because it's so much bigger than we are. Like, if you go outside and look at the ground, like, it just looks flat. You can't see the curvature of the Earth, really, because it's so big. So this inflation allowed the universe to get big enough that every place was flat enough for this to work. So it solved the flatness problem. It solved the horizon problem. We wondered where there's these things called a monopole. And they say, like, we should have these magnetic monopoles. We should be able to find them, and they're nowhere. We can't see them anywhere. Nobody's ever found a magnetic monopole. If you want to win a Nobel Prize, find yourself a magnetic monopole. You will get that prize. No one has ever found one. But they should be around. So the idea is maybe there were some magnetic monopoles that were created before this inflation, and then the universe kind of just zoomed into its big shape, and the magnetic monopoles got so spread out that it makes sense that we'd never find one. Because they're just really, really, really rare. Right? You had a couple of them hanging out, and then you spread them out over this big, big, big area. And so you're never going to run into one because they're just very, very rare. So we would get like a very low density of magnetic monopoles. And then the other one is, so I talked about how this cosmic background, it's 2.7 Kelvin just about everywhere, except there's little tiny fluctuations, right? Some parts are just a teensy tiny bit hotter. Some parts are just a teensy tiny bit cooler. And they're like, where did that come from? So if you go back and shrink everything down to before this inflation, there's something called like quantum uncertainties. And it's this idea that for a particle, you can never measure both its position and its velocity at the same time. If you know where a particle is, you can't know how fast it's moving. If you know how fast it's moving, you can't know where it is. You can really only measure like one at a time. And so there's this uncertainty, these little fluctuations that happen on a quantum level, just on a subatomic level. And if you have those tiny little uncertainties and then you blow everything up, all of a sudden those uncertainties got a little bit bigger, got big enough to be these fluctuations in the cosmic microwave background. Right? So it's just like if you have a balloon and you draw some little circles on the surface of this balloon and then you blow the balloon up, those circles that you've drawn on there are going to get bigger, right? Does that make sense? So in the same way, when it was teensy tiny, these little tiny cosmic or quantum fluctuations, when the inflation happened and this balloon blew up, those got bigger. And those led to the little fluctuations in the cosmic microwave background. And then those little fluctuations in the cosmic microwave background, those parts that were just a little bit hotter and just a little bit cooler, as the universe expanded, those fluctuations turned into structure. The parts that were just a little bit hotter had more density. So that's when stuff was close enough together that gravity could hold it together, and you started to get formation of stars and galaxies. And the parts that were just a little bit cooler had less stuff in them, and so that stuff wasn't able to pull itself together against the expansion, and you have these voids, these areas where there are not galaxies. Okay, so when we look at the big structure of the universe, like, you know, it kind of is these, you have these galaxies in these tendrils, we call them filaments, right? And you have all these galaxies inside here, and then areas where there's no galaxies. So these parts were the parts that were just a little bit hotter, and these parts were the parts that were just a little bit cooler.
We can kind of think about gravity as kind of like a magnet in that way, right?
Yeah, I mean,
how as it gets stronger, it starts to collect more, and as it gets stronger, it starts to collect.
They have very similar equations for the way that gravity and magnetism works. You know, if you have a little bit of stuff that clumps together because of gravity, now it has more mass, and it has more gravity, and it can pull stuff from farther away, and now it has more mass, and it can pull stuff from even farther away. But you have to have enough to start. You have to have enough to come together in the first place. And that happened in those little hot spots. And then as the universe stretched out, those hot spots got bigger. Okay? So, let's see. Oh, so what makes things expand? We don't really know, so we called it dark energy, right? We didn't know what dark matter was. We just knew it was some sort of matter, so we called it dark matter. Some sort of energy is making the universe expand. We don't really know what it is, so we call it dark energy. But it's most of the universe, right? So remember we talked about how we can talk about, you know, we can use E equals mc squared to convert mass into energy. So we can look at all the energy in the universe, and we can include mass in that. And most of the energy in the universe is this dark energy. It's like 70% of the energy in the universe is this dark energy. And then like 25% is dark matter. And then like 5% is the normal matter that you and I are made up of. And stars and gas and dust and all of that stuff is only 5% of all the energy in the universe. So the universe, I'm going to erase this. It started off really, really tiny, and then it had a big inflation where it got a lot bigger in a really short amount of time, and now it's just kind of slowly expanding. But they realized that the expansion is getting faster. So it started off really, really tiny, and then in just a little, really tiny bit of time, it got a lot bigger, right? It went from this big to being this big. And now it's getting bigger slowly. Right? But it's speeding up. And it's getting bigger faster as time goes on. So eventually, right, gravity holds things together, expansion pulls things apart. So eventually, expansion's going to win out as it gets faster. And things aren't going to be able to be held together. And things are going to cool down. Right? The more you have stuff clustered together, the hotter it gets. So as expansion wins out, things are going to get cooler. We're going to run out of dust and stuff. Stars aren't going to be able to form anymore. Yeah, and it's going to get dark. So that's kind of what we think is probably the final fate. Stuff's just going to be spread out, and it's going to be dark and cold. Okay? So, can talk about some of these homework problems. So, problem 4 says a period of rapid inflation in the size of the universe at very early times can be used to resolve 4 problems associated with non-inflation cosmologies. What are these 4 problems? Does anyone remember any of these problems?
The flatness of the universe.
The flatness, right. The horizon problem, that's another one. Sorry? The monopoles.
And then the seeds of the universe, or what is that? The seeds of the galaxies.
Right. So the seeds of the galaxy that come from the fluctuations in the cosmic microwave background. Right. So we've got the flatness problem. If the universe was just a little bit not flat, it would either have blown up and then crunched back down, or it would have expanded so fast that nothing could form. So we know it has to be flat. So inflation, it blew up really big and made everything flat. The rareness of the magnetic monopoles, the inflation diluted the monopole density down to where it makes sense that we wouldn't have found any. The density perturbations that eventually led to galaxy formation. So these were quantum fluctuations. That expansion blew into the fluctuations in the cosmic microwave background, which grew into the density fluctuations that led to galaxies forming. And then the last one is the horizon problem. The cosmic microwave background is the same temperature everywhere we look. And it wouldn't have been, 2 sides of it wouldn't have been close enough to be the same temperature if we didn't have this inflation. So, but with inflation, they were close enough, right? They were just right next to each other, and then they blew up in inflation, and now they're on 2 different sides, right? Sorry, what? Yeah. Well, so I'm going to talk about dark matter after this in a minute. So 5 says, what is the evidence for the acceleration of the expansion of the universe? So how do we know that it's getting faster? That this is going up? So when we can look at supernovas at really far distances, which means we're seeing them farther in the past, and we can see that the universe used to be expanding more slowly. So if it was expanding more slowly in the past, that means it's speeding up, right? So we use supernovas at large distances and see that the universe was expanding more slowly and it's speeding up.
Can you explain that a little bit more?
The acceleration?
Well, why would we know that?
We can see how fast things are moving away from us. So we look at like supernovas in really distant galaxies.
Supernovas are the brightest things.
Yeah, they're really bright in distant galaxies.
They're the most
And we can look at like, let me see. Why we use supernovas specifically is what you're asking?
Yeah.
Okay. Let me see if I can answer that.
If it takes too much time, I can just remember it, but
Okay.
it's helpful to
Yeah, no, like that. This doesn't. Okay, I will figure out that answer. Why we use supernovas specifically. But yeah, they did use them to find out that expansion was lower in the past. And if it was lower in the past, then it's faster now. Yeah.
Sorry. So let me finish this sentence because I didn't hear the rest of it. We can look at supernovas at far distances, so longer ago, and see.
That the universe was expanding more slowly in the past,
Yeah, okay.
which means and it's speeding up. So the when we look at ones from really, really far ago, it's expanding slowly, and then it's expanding faster, and how fast it's expanding is speeding up. So we know it's not just expanding faster, it's expanding faster and faster as time goes on.
So the supernovas grow, it's basically expand faster as time progresses eventually.
Yes, as time goes on, expansion increases, and we know that from looking at old things. So 6 says, is everybody okay to move on to the next one? 6 says, based on our current data and models, what is the most likely long-term fate of the universe? So our options are eventual slowing and the expansion and recollapse, called a big crunch, ever-increasing expansion rate, and a cold, dark universe.
Yes.
Yep. So the big crunch would happen if we had this closed, positive curvature universe. But we don't. We have a flat universe. Right? So the other options are radioactive decay of matter will light up the universe for as long as we can predict. That's not true. We know how long things take to decay. And then star formation in galaxies will keep the universe heated and light for at least the next 10 to the 20 years. So we talked about star formation is actually slowing down. Earlier on in the universe, there was more star formation. But the gas and the dust kind of starts to get used up because you form stars out of gas and dust. And the amount of stars that are forming slows down.
And the further we get away, the further galaxies get away from each other, slows down that star.
Yes, because when galaxies collide, you also have star formation. Yeah. So, 7 says, which of the following describes the large-scale distribution of galaxies in the universe? The options are uniform in all directions, clusters of galaxies, filaments, and voids. Yes, right? It looks like a big, like, blown up sponge, kind of. Like this, but 3D and all over. There's lots of pictures. I'll link to some more pictures when I put the video up so you guys can see. So the other options are uniform except for small density variations at the level of 1 in 100,000. And that's the cosmic microwave background. That is uniform except for these tiny little density variations. But when you blow that up, those variations stretch out and they turn into these filaments and clusters and voids. And then completely random, no.
So for these questions, there's only one right answer for 6 and 7?
Yes. Okay, so the other one is Big Bang Theory stuff. And then, okay, so we'll do dark matter. And then we can see if we have time to talk about some Big Bang stuff. Yeah? Okay. I'm doing a video to work out all the math problems that I'm gonna post tonight. So are there any specific ones that you guys wanted me to work out? Okay, I'll try to make it to 1 and 2. Okay.
Can you look over 12 if possible?
Yeah, like, you just felt like.
Okay, I'll see if I have time because that's more like Big Bang stuff. I will definitely do it in a video.
Where could we find the video?
I'm going to post it on YouTube tonight and I'm going to email it. I'm going to send it on. I'll do a Canvas announcement.
Dark matter?
Huh?
Dark matter?
I'm going to do all the math problems in a YouTube video.
And are you going to review other problems too, other than the math problems?
I'm going to put this video up, and then the one from like section tomorrow. And if there's anything I don't cover in those, then I'm going to put. So since if I don't get to like Big Bang stuff, then I'll do a video about that and put it up. Okay, so you guys okay to talk about dark matter real quick?
Yeah.
Okay, so we first learned about dark matter, that it existed from these galaxy rotation curves. So we measured how fast the stars in our galaxy were moving, and we saw something weird. We saw that the stars that were really far away from the center of the galaxy were moving a lot faster than we thought they should be. Right, so this is distance, and this is speed. So when we measure in our solar system, we measure how fast things are moving away, like how fast things are moving in their circles. We see something that looks like this. So the planets that are close into the center are moving really fast, and the ones that are far away are moving slow. But when we look at a galaxy, we see something that looks like this. The ones that are far away are moving a lot faster. And we can calculate how fast they should be moving by adding up all of the stars and the gas and the dust in the galaxy, right? That's what we think. Okay, galaxy is made up of stars and gas and dust. So we add up all the stars and gas and dust, and we say, okay, I know how gravity works, so I can calculate how fast they should be moving. And then we look at how fast they are moving, and we say, whoa, this is way off from what I thought. I'm wrong in my mass estimate by a lot. If the galaxy looks like this, there has to be a lot more mass that's not stars or gas or dust. And we were like, what else is there besides stars and gas and dust? We don't see anything else, right? That's all we see. So we don't see it, but it's there, so we call it dark matter, right? And it holds the stars in the galaxy together, right? Because we talked about escape velocity, right? Square root of 2gm over r. So these stars, they're at a big radius. So they should have a pretty small escape velocity. So if they go really fast, they should get flung out of the galaxy, right? They should be able to escape the gravity of the galaxy. Unless this mass is a lot bigger. If that mass is really big, then it will hold them in. So all that missing mass is this dark matter. And then we look at galaxies in clusters. And galaxies in clusters are moving too. And some of those little dwarf galaxies are moving really fast. And some of those should be flung out of the galaxy cluster, but they're not. So there's also this missing mass in a galaxy cluster. It's not just in the galaxy, it's in the whole cluster. And it's holding these clusters of galaxies together gravitationally. It adds more gravity and allows them to hold together. So that's the, like, on a single galaxy we see it. When we look at clusters of galaxies, we see it. And then when we look at the large scale structure, right, that filaments and voids, all these galaxies holding together and then these empty spaces between them, this shape would have never formed if there weren't more mass, right? We can do computer simulations and say, you know, what would the universe look like if we didn't have dark matter? And this shape that we see would never have formed. We only get a shape like this if we have dark matter. So we see evidence of this missing mass, this missing matter, on all three scales, on a galaxy scale, on a cluster scale, and then when we look and we zoom out and we look at, like, you know, each of these is a galaxy cluster in here when we look at the large scale structure of the universe.
It just seems crazy that we don't see it in our solar system too.
We do, it's there. It's just not, doesn't have like they're not enough that there's like the gravitational effect of it. Right. It's everywhere. There's dark matter in this room.
Oh.
But it just kind of goes right through you. Like, we don't interact with it. Light passes right through it. So that's one thing we knew, right? Is that light passes through dark matter. It doesn't absorb light. It doesn't create light. Like, you know, stars create light. Gas absorbs light and then re-emits light. Dust can absorb light. It can reflect light. Like, light can bounce off of it, right? So all these things, stars, gas, dust, they all interact with light, right? They either make it or they absorb it or they bounce it. But dark matter doesn't do that. It doesn't interact with light except in one way, and that's through gravity. So we talked about this idea of gravitational lensing, right? Where a lot of mass can create a warp in space-time that bends light. And light will bend around dark matter. And that's the only way that it interacts with dark matter, is through gravity. Dark matter doesn't emit light, it doesn't absorb light, it doesn't reflect light. It just bends it sometimes if there's enough dark matter.
And when you say light, you're talking about all of the varieties of these electromagnetic.
Yeah, the whole electromagnetic spectrum, from gamma rays to X-rays, including visible light, including radio waves, including everything. And that's why we don't see it, because we see light, right? So we see stars because they give off light. We see dust because it reflects light. The only way we know these things are there, are either we see them with light or we see them with gravity. And dark matter, we can't see it with light because it doesn't interact with light except through gravity. So we see it through gravity, right? We know it's creating this gravity to hold the stars in our galaxy.
Can we pinpoint it with gravity though?
What do you mean?
You say we see it with gravity. Like, can we say at this point in the sky, universe, whatever,
Yeah, I mean, with gravitational lensing, we can find like areas that have more dark matter than others. Absolutely.
Okay.
Like that's how we know that certain that's how we know that some dwarf galaxies have a lot of dark matter in them, because we can see the way they affect their gravity. Okay, so yeah.
When you said it just bends light, if there's enough dark matter, what is it?
The dark matter will bend the light
If there's enough dark
if there's enough of it, right? So so we know that it doesn't really interact with light. And another thing that we know is that it's they call it cold. It's not moving very fast. And so we tell where it is based on how it affects other things' gravity, how it affects gravity. The only way it affects light is through gravity, and we know it's not moving very fast. It's cold. So, going over the homework problems, 3 says dark matter has been invoked to explain 3 observations on very different spatial scales. What are these observations? So what are the 3 scales? Right. On a galaxy scale, there's a flat rotation curve, right? This is essentially flat. So like this is the Milky Way, and we look at other galaxies, and they all kind of look like that. They all flatten out. This flat rotation curve on the scale of a single galaxy gives us evidence for dark matter. What was the next scale?
Galaxy clusters.
Clusters, right. When we look at clusters of galaxies, they're held together by dark matter. Little like dwarf galaxies and stuff would fly off, just the way that stars in our galaxy would fly off. But they don't, because you have enough dark matter. And then the last scale?
It's the large scale structure.
Right, this large scale structure. The simulations show it only forms if you have dark matter. Okay, so those are our 3 scales. On a single galaxy, the flat rotation curve.
And that just being found in other spiral galaxies.
Yeah. Every spiral galaxy that we see shows this flat rotation curve. So on the scale of a single galaxy, you have a flat rotation curve. On the scale of galaxy clusters, the clusters are gravitationally held together by dark matter. And on the scale of the large scale structure, you only get that formation when you have dark matter in your model. So we can look at problem 8. Which of the following are thought to be properties that are true of dark matter? So it is cold.
True.
Right? It's true. It does not readily interact directly with photons or other matter.
True.
That's true. So it has a small cross-section for interaction. Just means that it doesn't really interact with photons directly. It does not emit or absorb electromagnetic radiation.
True.
That's true. And it is primarily inferred by its gravitational effect on other matter.
True.
That's true. Okay, so I think that's all the dark matter ones.
There's like 1 on 9 where it says dark matter is much more common than other types of matter.
Oh yeah, that's kind of a Big Bang one. I'll go over that one. So there's one that I guess I skipped earlier, talking about so kind of going, I'm going to go back and do, there's 2 questions kind of on inflation and stuff that I'm going to talk about, or that we can go over real quick. So question 18 says, which of the following describes the horizon problem in cosmology? So the cosmic microwave background is at a uniform temperature over the entire sky, yet regions separated by large angles would not have been in causal contact in a universe that had expanded uniformly since the Big Bang.
Yes.
True. Yes, that's the answer. The other options are we see the same galaxies looking directly forward and directly back because light is curved around the universe, which confuses investigations of large-scale structure. That is not true. That is just not something that we see. And then if the universe were not spatially flat, it would have collapsed back on itself. That is a true statement, but it is not the horizon problem.
That's a flatness problem.
Right. So because of the curvature of the universe, we cannot see a large part of the observable universe. Well, so we can't see a large part of the observable universe because we can only see as far as light's gotten to us. Right? Like light that was emitted at the beginning of the universe reached us. And if the universe is bigger than at distance it took for that light to get to us in the time, then we can't see past it. But that's not the horizon problem. The horizon problem is that the cosmic microwave background is the same temperature everywhere, and that doesn't make sense without inflation. So the theory of cosmic inflation, this is 19. Okay, sorry, the video cut out. I'm going to finish that homework problem in this video. So this was problem 19. The question is, the theory of cosmic inflation was originally motivated to understand why magnetic monopoles were so rare in the universe. What other cosmological puzzles does inflation resolve? The first one is that we appear to live in a spatially flat universe with omega total is equal to 1. That's true. The second one is the energy released during the inflationary period that resulted in the formation of the light elements hydrogen, helium, and lithium. That is not true. The growth of quantum fluctuations during inflation provided the small fluctuations in the cosmic microwave background that were the seeds of galaxy and structure formation. That is true. Right, that's one of the things that was solved by inflation. And then inflation allows us to understand what existed before the Big Bang. That is not true. We still don't know what happened before the Big Bang. Okay, so that is all I have for this video. The rest of section did not get recorded, but I am going to record section tomorrow and also maybe make a video on the early stuff in this part, like fundamental particles and stuff like that. So I hope this was helpful to you. If these videos have been useful to you guys, or anything that I or Dave have done has been useful, please, please, please make sure to fill out your evaluation forms for the TAs and for the class. Those are really useful to us to get some feedback and see what we're doing well and where we can improve. And yeah, I would be very grateful if you guys would fill those out. So that's it for this stuff, and good studying for your quiz. I'm also putting a couple links to some simulations in the description for this video. So there's a couple really cool simulations about different ways that we detect exoplanets. There's one for transiting planets that you can see if you change the size of the planet or the size of the star or how close it is or how big it is, how far away it is. You can see how that affects the light curve of the star. There is one for the radial velocity where you can see how changing the size of the star or the planet changes the how much the star moves. So if you play around with that, try increasing the size of the planet a bunch and decreasing the size of the star, and you can really see how the star moves in that rotational thing. And then I've also done, there's one in there about the habitable zone, and you can see how if you change the temperature and the type of star and stuff, then it will move the habitable zone. So check those out. They're pretty cool. And good luck.